Okay, welcome back again. This lesson we are looking at something we call Le Chatelier's principle. Okay, this is obviously named after a French person, and we're going to look at what happens when we disturb or change an equilibrium, a system at equilibrium. So, a lot of kind of visuals that are hopefully going to help in this lesson, and something that we'll certainly need to go over a little bit together in class. There's a few things that we'll kind of mention that we don't need to go into as much detail this time around, and certainly please ask as much as you need to in class. So Le Chatelier's principle basically states that when you have a system that's at equilibrium, so remember system at equilibrium, we've got our reactants being converted into products, and at the exact same time, at the exact same rate, our products are being converted back into reactants. There's a lot of criteria for that. So when we have a system that exists that way, right? Think about the ants moving piles of stuff this way and back. Well, what happens if all of a sudden we change that system? What happens if we come along and we dump a bunch of stuff on one side of those piles? So when we make a change to a system at equilibrium, and we're going to call that a stress. When there's a stress imposed on a system, which is in other words, it's just a change. What happens is that equilibrium is going to adjust. It's going to counteract that stress or that change to try and undo what was done. Okay, so what we do to a system at equilibrium, naturally it tries to undo, to get back to that nice balanced. Remember, equilibrium being a balance, it tries to get back into balance somehow. Okay, so a system at equilibrium, if it's subjected to a change or a stress that's imposed on it, processes will occur, and that's just a wordy way of saying things happen, to counteract or undo that change. Okay, so there are a lot of things we're going to talk about. Here are a few really quick examples, and we're going to look at many of these in more detail. So for example, if you add heat to a system, if you heat it up, if that system's at equilibrium, then that system's going to try and cool itself back down. So we're going to try and undo that change that was done. If we increase the concentration of a species in a system at equilibrium, then that system's going to try and reduce the concentration. It's going to try and use up what we add, that sort of thing. So don't worry about memorizing these all on this slide. We're going to see many of these in more detail. So here's a really good analogy for one of the changes to a system we can make that's at equilibrium. So imagine we have this system at equilibrium, right? We've got this system in balance, okay? So our little ants moving back and forth, we got the forward rate and the reverse rate happening at the exact same time, at the exact same rate. So these concentrations on either side would remain constant, they wouldn't change. That system would be nicely balanced, let's say. So I want you to imagine what happens if we take this system in the top. Imagine these are my reactants on the left, my products on the right. What happens if all of a sudden we dump in some stuff on the right-hand side? What happens if we add some stuff to the product side? Well, all of a sudden you can definitely see or hopefully imagine that we're not out of balance. So all of a sudden we are not in balance, which means we are not at equilibrium anymore. Equilibrium has to be that balance of reactants and products in the forward and reverse rates. So we're definitely not at equilibrium anymore. So how does this system here get back into balance, get back to an equilibrium where they are nicely balanced? And the image here shows, well, what if some of the stuff that was added, some of those weights, whatever they are shifted or moved from that right-hand product side to the left-hand reactant side? So what if some of those are shifted from right to left? And then we end up here. So even though we end up with a system that has more stuff than it used to, these didn't used to be there, we do end up with a system that's nicely balanced. So we are now at equilibrium. And it's a new equilibrium. It's not the exact same as it was up here. It's different. We've got more things in there, but we're balanced. Okay, and this is this visual kind of highlights Le Chatelier's principle in a few images. When we change something, we add it. Well, something needs to happen. Something needs to change, and there's that counteraction, that undoing of what we did to try and shift things around to try and get back to balance. Here's another analogy. We've got a system at equilibrium. We've got, you can think about your reactants and products here. This is a little bit misleading because the amounts don't have to be equal. They just have to be constant. So what happens if all of a sudden I add some material, in this case on my reactant side? Well, we're not at equilibrium anymore. Things are not nicely in balance. So the shift, the response, or I'm going to use the wording, the shift that's going to occur is some of these materials that were added are going to need to be shifted to the product side so that we get back to a nice balance. And that's a system that's reached a new equilibrium. We're back to a balance. So concentration, that's really what we were just looking at. So when you add some reactant, so let's imagine we have this system at equilibrium, and I all of a sudden increase the concentration of A. So I dump in some more A, whatever that happens to be. Well, that means I'm not at equilibrium anymore. And the reason for that is all of a sudden, if you've got more A available, then that means the collisions between A and B are going to increase. They're going to be more frequent because you got more A in there. All of a sudden, you got more reactants. So all of a sudden, you got more reactants colliding. So your forward rate is going to actually be faster for a little while. In that forward direction, some of this A that you added, so this is what we added, it increased the concentration. In order to use up the A that we added, this system shifts to the right-hand side. And really, when we say shifts to the right-hand side, all we're saying is that that forward reaction is going to use up some of the A we added. Not all of it, but some of it. That means that we're going to use up some A, we're going to use up a little B, we're going to form more C and more D. So the analogy there is if you're on the teeter-totter and you got A and B and C and D, well, if all of a sudden you add more A, you need to send it to the right. And how we do that is by performing the forward reaction. So we're going to use up a little bit of A, use up a little bit of A. We're going to use up a little bit of B. We're going to form more C, form more D. And that's our forward reaction that's happening at a higher rate. And that's to try and get us back to an equilibrium. That would be a shift to the right. Okay? If we think about adding a product, so adding a product, let's say there's nothing stopping us from taking this system at equilibrium, this teeter-totter. We could easily increase the concentration of D as well instead of A. So increasing concentration, all of a sudden you have too much of this product around, whatever that happens to be. So that concentration increases. This system will adjust for that by shifting some of that to the left. So that system's going to shift, that equilibrium's going to shift left. When it shifts left, it's going to use up some of this product D. It's going to use up some, not all of this product C. And we're going to get more A. So we're going to form more A and more B. Okay? What happens if we remove some product or reactant? And it's really just the opposite. So imagine your teeter-totter. What happens if you came along and you actually removed some weight from this teeter-totter? So if you removed some weight from this teeter-totter, then all of a sudden you're going to shift, or you're going to be out of balance. So how does that system get back into balance? It gets back into balance by taking some weight from the right-hand side and shifting it to the left. Okay? If it shifts it to the left, it's going to make more of what we took away. So always try and focus on how do we undo what we just did. So if we remove, let's imagine removing some A. So we have less A, this reactant on the left. So the stress was to take away some reactant. That means that that system has to undo that. How do we get more A? Well, we get more A by performing the reverse reaction, because that's what will increase this. So that's going to be our shift. That's how we decide on the direction of the shift. So concentration example here. Here's a system at equilibrium in a closed system, super important because nothing's escaping or getting in. Suppose some additional hydrogen gas is suddenly injected in. So all of a sudden we increase the concentration of hydrogen gas, okay? And that's the stress, the change. So our system has to adjust for that by shifting to somehow undo what we just did. So it needs to use up some H2 instead of adding it. So we added it. How does the system use it up? It uses up H2 by performing the forward reaction from left to right. Okay, so we're going to shift to try and decrease or lower the hydrogen concentration. So how do we use up hydrogen gas? We use up hydrogen gas in the forward reaction. So this equilibrium will shift. So the forward reaction is left to right. So it's going to shift to the right, the product side, to try and use up some of what we added. Okay? So that means, so try and think about what happens in the end. So when we're shifting to the right, we're going to use up some of the H2 that we added. What's going to happen to I2, the iodine? Well, since the forward reaction is dominating here, we're going to use up some of the I2 as well, because it's also a reactant. Now I want you to think what happens to this HI, the product. Well, if we're shifting in the forward direction, my forward reaction uses up reactants and forms products. So we are actually going to make more HI because it's on the product side. Here's a visual of an example like that. So section A, like time A in here, is my system that's already at some sort of initial equilibrium. Notice those concentrations are constant. At time 1, I want you to notice what happens. At time 1, this concentration of H2 spikes up. It instantaneously goes up. So that was me adding hydrogen to that system. Okay? Nothing else changed immediately at time 1. So notice what happens after that. So after my stress of adding H2, so notice that this system kind of compensates for that by shifting to the right, we said on the last slide. And shifting to the right uses up H2 and I2. So that's why we see their amount curves gradually decrease in that same shape we've always seen, quickly and then slower and slower. But shifting to the right forms my product HI. So we see the product curve do the opposite. It increases. Okay. Eventually, we're going to get back to some sort of balance, which is constant concentrations. Okay. So the stress is being reduced as H2 is used up. I2 is also used up because it's also a reactant. HI is being formed. Okay. At time 2, we've reached a new equilibrium where we have constant concentrations. Okay. Concentration rule, increasing the concentration of something. So let's think about general example, increasing the concentration of A would cause a shift to the opposite side. So if I increase A, we're going to shift to the product side to use up some of the A. If I decrease the concentration of A, then that system's going to shift to the same side as it. So lowering the concentration of A is going to cause a shift to the left to try and make more. It's trying to undo what we just did. Please note that we can only adjust the concentration for aqueous and gaseous species. We cannot change the concentration of solids and pure liquids. So if one of these reactants is like, a piece of solid magnesium, for example, then we can't change its concentration. So we can't be talking about, we'll increase the concentration of Mg, because it never changes. It's constant. Okay, temperature. Let's tell you this principle in temperature. My advice would be think of heat in your reaction as a reactant or a product. So in this case, in this example, we have heat on the left hand, the reactant side. So think of heat being needed to be added as a reactant to get that reaction going. So if you increase the temperature, then you're increasing the amount of heat. So you have more heat. So that system needs to somehow adjust by using up heat. You heated it up, it tries to cool itself back down. So if we increase the heat, there's my stress. This system will adjust by taking what we added, which happens to be heat, and trying to use it up. This example does that by shifting to the right-hand side to use up the added heat. So that'd be a shift to the product side. If we decrease the temperature, then you are removing heat, which in this case, treat it like a reactant. So if you remove heat, this system tries to heat itself back up. So which reaction, forward or reverse, will produce heat, which will produce more heat, and that's going to be a shift to the left, okay? And that's going to increase the temperature back up to adjust for the change that we've imposed. Here's an example here. So again, we have a system at equilibrium during time A. At time 1, T1, we've increased the temperature. Notice at time 1, nothing spikes up immediately. Nothing goes straight up or straight down because it takes time to adjust. So let's look at this example at the top. My heat is on the right-hand side, okay? That's a product, that's exothermic reaction in the forward direction. So if we increase temperature, notice what happens. If I increase temperature, we add heat to that system, then this system has to adjust by somehow cooling itself back down. So which reaction is going to kind of overtake the other? Which one's going to dominate? The forward reaction will make more heat, and the reverse reaction will use up some heat. So we're going to be looking at a shift to the left. Okay, a shift to the left will use up some of the heat that was added, okay, because the reverse reaction is endothermic, okay. In the reverse reaction, what's going to happen? Well, that means if we're trying to use up heat that we added, then that means this PCl5 will also be used up because it's on the same side, and they shift to the left. So we're going to form more Cl2 and form more PCl3. So this is why you see the curves do what they do. So this is why the curve for PCl5 goes down. Okay, because it's being used up. And this is why the curves for Cl2 and PCl3 both go up, because they're on the opposite side. Okay, it's shifting in the direction of those, so we're making more. The rule for temperature, when you have a heat term on the left or right, I'll just put it on the right in this example. So if you increase temperature, you're going to shift away from the heat term. And that's because it's trying to use up the heat you added. And if you shift if you decrease the temperature, you're going to shift towards the heat term to try and make more up. So that's a kind of a good way to decide on the direction of the shift there. Pressure. Okay, when we're talking about pressure, we're really talking about adjusting the concentration for gases. Okay, so remember the relationship between pressure and volume, right? If I decrease in order to decrease the pressure or increase the pressure, we're talking about adjusting the volume. Okay, so in decreasing volume would be an increase of pressure, and increasing volume would be a decrease of pressure. Okay, so let's look at gases. So if I increase the pressure, that means I decrease volume. I have less space available. Okay, what's going to happen if I have less space available? Then this system is going to shift towards the side that occupies less space. So it's going to shift to the side that has less gases, because less gases will occupy less volume. So up in my reaction, I've got gas, 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 gas. They all happen to be gases. So on the left, I've got 2 and 1 more. So I've got 3 moles of gases. On the right-hand side, I've got 2 moles of gases. Okay? So in this case, on the left-hand side, increasing the pressure, I shift to a side with less gases, which would be the right-hand side, the product side. Okay? Decreasing the pressure. If you decrease the pressure, you have more volume, more space available, and that system's going to shift to the side that fills up that added space. So if you increase the amount of space available, then the system will shift to fill that space. So it's going to shift to the side that makes more moles of gases, which in our example up here would be the left-hand side. Okay? Increasing or decreasing volume, do the exact same thing we just did. So here's an example, same reaction from before. Okay. Now notice, don't worry about drawing these. It's not something that we kind of have the time for. So if you're kind of having trouble kind of thinking, well, how do they draw exactly what's going on? We just want to be able to kind of look at them and try and figure out what's going on. So at time 1, this system that was at equilibrium, the pressure was increased. And I'm going to be able to decide that because notice what happens. All of these concentrations spike up. There's an immediate change. So I know that this wasn't a temperature change because temperature changes are gradual as things have to try and heat themselves up. So all of a sudden, all of the concentrations spiked, which means I went from a larger volume to a smaller volume. Okay? A smaller volume means an increase in concentration. Okay? So that is an increase in pressure. Okay. So all of these, where are we? All of the gases increase their concentration. That's at time 1. Okay. So in section B, that time period, things are happening to adjust for that. So let's think about this. We've decreased the volume, so less space is available. So this system will shift to the side that has less gases. So all we have to do is look at our reaction, the left side and the right-hand side. We've got 1 mole of gas, another mole of gas. I've got 2 moles of gas on the left-hand side. On the right-hand side, I've got 1 mole of gas. So which side has less? Well, it's obviously a product side. So we're shifting to the right. Okay? If I shift to the right, then that means I'm going to get more of the things on the right, which is why you see over here the PCl5 curve increase its concentration. And when we're shifting to the right, we are using up some of these reactants, which is why you see their curves decrease and they go down in concentration. Eventually, we reach a new equilibrium at time 2, where things level out and they have constant concentrations. The rule here for pressure or for volume for our gases, so an increase in pressure, so that's a decrease in volume. will cause a shift to the side with less gas molecules, and a decrease in pressure, which is an increase in volume, will shift to the side with more gas molecules to fill that added space. Okay? Here's a visual of that. So we have this initial system at equilibrium that occupied a certain amount of space. If I decrease the pressure, moving to the right, which is an increase in volume, then what happens is that equilibrium is going to shift to the side that makes more gases to fill that space. So if you count up your red and green molecules here, or atoms, then notice we're shifting to have more of these A molecules, the red ones, because that's the side that has more gases. If I decrease the volume or increase the pressure, then we're going to shift, so we've got less space. We're going to shift to the side that occupies less space, which is less gas molecules, and in that case, that's a shift to the right-hand side. So that's kind of how we're going to decide on the direction of the shift for pressure changes. This slide here, you can pause this, look at this in your notes really carefully. It's just really just a summary of kind of what we looked at for each of those three changes. And last thing here, catalysts. We know that catalysts are going to speed up a reaction, and we can do this very quickly because a catalyst is not going to shift your equilibrium at all. So when you have a system at equilibrium, we know that a catalyst can take that equilibrium system, it can make that forward reaction easier to occur. It can lower the activation energy, but it also does it for the reverse reaction. And it does so by the exact same amount. So it speeds them up at the exact same rate in the forward and reverse direction. So we don't see a shift, okay? Both of the forward and reverse reactions speed up in the same way. There's no shifting left or right. So it doesn't actually change your equilibrium. It just gets you there faster. So it just gets you to equilibrium quicker than if you didn't have a catalyst. Okay, so no shift. So anytime you're asked about a shift with a catalyst, there is no shift. It just makes it occur faster. Okay. Again, here's a summary of the changes in terms of what temperature, concentration, and catalysts do. We will go over this obviously a little bit together, but certainly the background here is going to help you with that. Again, here another table just summarizing the shifting when you increase or decrease things or add things and so on. Okay, and a very quick explanation why. Okay, so we'll look at this together a little bit. I'm going to stop there and we'll try some of the questions on this section.